So the very last thing that I wanted to do is I wanted to look at two examples of drawing Lewis structures and kind of just bring everything that we've been talking about all together. Formal charges, resonance, exceptions, everything. Because as you know, chemistry, it gets complex, and so typically you don't see things in isolation; you see them all together. So consider the polyatomic ions for sulfate, which is SO4 with a -2 charge. The question is, what would be the best Lewis dot structure? So let's just start out with what we know. We need to count up the total number of valence electrons. So sulfur is going to have 6. Oxygen also has 6, but there's 4 of them, so that's going to be 24. And then you have 2 extra electrons because of the -2 charge. So we have 32 valence electrons at our disposal here. So we're going to start off. Sulfur's in the center. You have oxygens, 4 of them around there. So we're going to start off with doing single bonds for all of our oxygens. So that takes care of 8 valence electrons. So out of 32, we just use 8. So now we're down to 24. Let's take care of our oxygens. 2, 4, and 6. 8, 10, and 12. 14, 16, 18, 20, 22, and 24. So we just took care of all the oxygens using 24, so we have 0 electrons left over. All the oxygens are satisfied, as well as the sulfur is satisfied. So all of our atoms, I just went through those those lone pairs, sorry about that. All of our atoms actually are satisfied, and so this right here is a valid Lewis dot structure for the sulfate ion. So if you put this on an exam, this is a 100% in terms of drawing a correct, successful Lewis dot structure. Is it the best one? No, and here's why. Remember, what is the formal charge for an oxygen atom in the terminal position when it is singly bonded? The answer is -1. So all of these oxygens have a -1 formal charge, every single one. And then for sulfur, sulfur has 6 valence electrons minus, how many things are touching this sulfur? 4 things, 4 lines. So 6 minus 4 is +2. So here's our formal charges. First of all, every single atom has a formal charge. And second of all, you have a +2 in there. That's kind of high. That's pretty large. So we don't like that. Is it correct? Yeah, because look at all your net charges. 2 negatives would be canceled out by the +2 from sulfur, and so you'd have -2 left over, which is the overall charge. So it's right, but like I said, structures don't usually like to have a lot of formal charges, and it especially doesn't like to have large formal charges like + or -2. So what are our options? You might be thinking. You're like, well, what can I do? Remember the exception that sulfur, since it's in row 3, sulfur actually can have an expanded octet. So because it can have an expanded octet, it actually can take some electrons from one of the oxygens and turn it into a double bond. So I'm just going to choose the oxygen that's on the right here, and I'm going to take these 2 electrons right here, and I'm actually going to move them into a double bond. So here's what you'd actually end up getting once you do that. You'd end up having a double bond now between sulfur and this oxygen over here, and then you'd end up having the other oxygen still be single bonded. So you get those added in here. All right. So now, after doing that, these oxygens still have a -1 charge. This oxygen is now 0, and sulfur is now 6 minus, now how many things are touching this sulfur? 1, 2, 3, 4, 5. So 6 minus 5 is +1. So what have I just done by doing that? Not only was I able to get oxygen's formal charge down to 0, which it likes, but I was able to reduce that +2 down to a +1. That's a double whammy. That definitely makes it much better than what we originally had. But who's to say we have to stop there? Couldn't we do that again? And the answer is yes. So let me right now I'm just choosing randomly. Let me take electrons from this top oxygen, so let's say these ones, and move them also into a double bond, because sulfur can have an expanded octet. So if I do that, and let me see if I got some space to do it right here. Now what I have is a double bond to this oxygen up here, the double bond that we originally made over here to the right, and then the other oxygens are still singly bonded. Okay, so these oxygens right here, and I'm being lazy, I'm not showing the brackets. I should be having, oh, it did it again. Sorry about that. Sometimes the pen freaks out. It should have brackets around here. There we go. 2 negative. Let me see if I can clean this up a little bit. Actually, I'm just going to rewrite that. So yeah, it should have brackets. But the key thing I want you to see is that what happens now with the formal charges? Well, this is still -1. This is still -1. Both of these oxygens being doubly bonded are 0. And now look at sulfur. Sulfur is 6 minus, how many things are touching this sulfur? 6 things. And so, by effectively making 2 double bonds, of which are allowed because sulfur can have an expanded octet, I have now reduced 3 of my elements all to have a 0 formal charge. That's good news. Now, watch out, because you may be thinking, well, I like where this is going. Let's do it again. So you might actually be saying, can I do another double bond? Well, let's see what would happen if I did that. If I did sulfur, I have this double bond, and then let's say I did a double bond over here. Because you're like, hey, I like when oxygen doesn't have a formal charge. That's good news, right? Okay, well, let's see what happens. So now you have oxygen down here is the only one that has a single bond. So that's going to be negative. The good news is all of these oxygens are 0. But what's sulfur now? If I do a formal charge for sulfur, 6 minus, there are 7 things touching this sulfur. Okay, and so that is -1. Here's where you know you've gone too far. Remember that rule that I said with formal charge that the most electronegative element should be the most negative? Why is it that sulfur is negatively formal charged while these oxygens are 0? Oxygens, being the most electronegative elements, should be the ones that are the most negative atoms in the molecule. Sulfur should not have a positive. So I've gone too far there. That's how I know that doing 3 double bonds is too much. I should have stopped up here with the 2 double bonds here. So this actually right here is the best structure. And I'm putting my brackets around it. Okay, so not this one, not even the first one. Although they are valid, I want to point that out. They are valid Lewis structures. They're not the best Lewis structure. It's the one that has the 2 double bonds. However, do you see what kind of fun we've got ourselves into? Resonance, okay? Even though it's the best structure, there are resonance structures that go with that. And because there are 2 double bonds, there are several ways that those double bonds could be oriented. I'm not going to draw them all because that would get very crazy in the little amount of space that I've left myself. Actually, let me do this. Let me try to free up some space. I'm still not going to do it just for timing's sake for the video, but I just want to show you how would you draw those resonance structures. Well, here's what I do. You've got sulfur. Okay, so you've got the double bond on the top. Originally, you had the double bond to the right, but you could have the double bond down that way, so that would be another one. You have sulfur double bond on top, but the double bond could be on the left. You could move the double bond that's up here. Originally, there was a double bond to the right, but now the double bond is down this way. Sulfur originally had a double bond to the right, and it could be this way. Okay, and then finally, the double bond could also be, gosh, where is it at? Where is it at? Let me see if I can figure it out. Oh, here it is. You could have the double bond on the top. Nope, we already have that one. Oh, I know where it is. Sometimes when I'm drawing using this little ink pad, it's not as easily for me to see it. But you could have it like that. So I just kind of look at where the double bonds are. I don't want to complicate things yet. Then I'll plug in all my oxygens and all my electrons. Was this a tough one? Of course it was. This would be something that would be definitely extra credit for sure. Which, by the way, I do give extra credit if you show the best resonance structures. Because remember, I said that first one was valid, and if you did that, you would have gotten 100% for that question. But if you draw the best resonance structures, where they're applicable, you do get extra credit. So keep that in mind. But this would be the best structure here, and you'd have to draw those 6 resonance structures. Let's do one more, and this one actually is going to be a little easier. If you'd like, go ahead and pause the video and try doing this on your own. I'd like you to draw the best resonance structure for phosphate, and then hit play to reveal the answer. So go ahead and do that now, if you'd like to. All right, so regardless of whether you tried that on your own or you just want to watch, we know phosphorus is in the middle. You've got 4 oxygens that are around it. Let's see, phosphorus is 5 valence electrons, oxygen is 6 times 4 is 24, plus 3 extra electrons for the charge. We are looking at 32 electrons. Single bonds to all my oxygens takes care of 8. So 8 electrons from 32, that's going to give me 24 left over. Take care of my oxygens first. There's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. So I satisfied all my oxygens. My phosphorus is also satisfied. So put brackets around here, put the charge on the outside. This is a valid Lewis dot structure. This will get you 100% on the test for this question. However, this is not the best structure, and the reason why is because if I assign formal charges to every single one of these oxygens, they're all -1. And if I assign formal charge to the phosphorus, 5 minus 4, that's going to give me a +1. Every atom has a formal charge. Let's see if we can get rid of that. Ask yourself, can phosphorus have an expanded octet? Is it even allowed? The answer is yes, because it is definitely in row 3 or higher. So, because it can have an expanded octet, let me take 2 electrons from any oxygen, doesn't matter which one. I don't know why my habit's always to go to the one on the right here, so I'm going to do that. I'm going to take these electrons right here, and I'm going to stick them right there. And by doing that, that's going to change my structure to this. Double bond over here to this oxygen. Single bonds to all the other oxygens. And what have I effectively done by doing that? Well, the double bond between the oxygen and the phosphorus, that has a 0 formal charge on this oxygen, as well as now I have a 0 formal charge on this phosphorus. And then the oxygens that are left over all have a -1, which totals the total -3 that I should have for the phosphate. Now I want to stop there. I don't want to do any other double bonds, because if I do another double bond, phosphorus will now have a negative formal charge. And I don't want that because phosphorus is the least electronegative element. So this actually is the best structure. However, you can see that there's resonance. I could have picked any of those oxygens to do the double bond. And in fact, all of them are existing at the exact same time. So there would be 4 resonance structures total. One with the double bond over here, one with the double bond on the bottom, one with the double bond on the left, and one with the double bond up on top. So I'm not going to draw those right now, but you would have to draw all of those on the exam. And not only would you have to draw those on the exam, you need to make sure you show the formal charges for every single one. So let me just show you, I'm not going to do it for all of them, but let me just show you, for example, this one. Okay, so I'm redrawing it. And it doesn't take that long, actually. Like I said, once you know what you're doing, you know kind of how many electrons need to go where. It's just more time consuming, if anything. Okay, it still needs to have brackets around it because it's an ion. Kind of run out of space here, 3 negative. But I need to show -1, -1, -1. I need to show that for every single form of the resonance. Even though you're like, well, isn't it assumed because I wrote it over here? No, you need to write it on every single atom. It takes literally like 3 seconds, so it's not that big a deal. But make sure that you do that. But that is how you can use formal charge and exceptions in resonance to figure out what the best structure is. So hopefully these videos have helped you, and then just continue to do practice, and you'll start to see patterns and trends, and you'll definitely see yourself taking less time to do these structures.